In this bonus video, we're going to be talking about the basics of complex numbers. This would match up with Appendix Part 7 in our textbook. And I'm covering this because it doesn't appear to be a required topic in this course. It doesn't show up in any of the main book sections because it's only in an appendix. But I think it's necessary to cover it here in this class if it's not done in the second part, Pre-Calculus 2. Complex numbers have more properties than we're going to be going over in this video because some of those properties require knowledge of the coming sections in Chapter 5, but also some of the work that would be done in the second class dealing with sine and cosine and trigonometry and stuff. So we'll start off with what they are. The complex numbers are a number field. Which means two things. It's a number field because it has numbers in it. We treat them as numbers as opposed to some other mathematical object. For example, polynomials are mathematical objects. They're structures, and if you put a bunch of them together, you can create a field under certain conditions. And we're calling it a field because we're able to do all four of the basic mathematical operations on it. You see, in algebra, there are a couple of structures which are determined by what kind of operations you can do. For example, if you can only do one thing, well, you can always do more than one thing. If you can only add and subtract, then you would have what's called a group. Similarly, if you can only multiply and divide, then you have what's called a group. An example of a group that we have is with addition and subtraction, all of our whole numbers or natural numbers. That's not entirely true. It could be because we're not allowed to do all of the subtractions with whole numbers. We need negative numbers, so we need integers. So that's going to be kind of our first problem that we're addressing is when you restrict yourself to a certain set of numbers, you can't actually do everything. So you got to go up one by introducing even more of them. So the whole numbers and natural numbers, they're not enough because I don't always get an answer when I do a subtraction. So I go up one more. I go to the integers that has positive numbers and negative numbers. And there I'm allowed to add and subtract any two numbers and I'll get an answer. It'll be positive or negative, or it could be 0. But something you can do in the integers as well is you can multiply in addition to the addition and subtraction that we already had. So I would call it a ring, which is kind of a basic structure. I can add, subtract, and I can multiply things. And I can sometimes do a division, but it doesn't work all the time. For example, I can't take 2 and divide it by 3 because that answer is not going to be an integer. I don't have enough numbers. So I add in more numbers and I get the rational numbers, all of my fractions. And that's the first group of numbers that I have where I get a field. So I'm going to write the natural numbers are contained in the integers. We use a Z for that because there's a German word. And those are contained in the rational numbers, Q for quotients. And those are contained in the real numbers. See, if you do enough work with rational numbers, you find out that there are some numbers that are missing. For example, if I'm looking for the roots of a polynomial, x squared minus 2 equal to 0, that's kind of the same thing as saying x squared equals 2. This has no answers in the rational numbers. So here, because of polynomials, I realized that my rational numbers aren't enough, even though I'm able to do all 4 of the operations. So I need to include more. There's actually an extra number field that's squeezed in between here, because the next one up would be the set of constructible numbers, which is a bunch of rational numbers and some of the real numbers, but not all of them. But the next step up, really, from rational numbers is the real numbers, where we have the real line continuum situation. And I have all of those numbers with infinitely long decimal representations. But those still aren't enough. Oops. And the reason for that is if I want the square root of -1, basic situation that we have, I can't find an answer in the real numbers. So this has no answer in the real numbers. And this is where the bad jokes start. Since the square root of since the square root of -1 has no real number answer, we say that it's imaginary because it's not real. I like to call them fake numbers just because of that. So this is the imaginary number. Not writing very well. And once I include the imaginary number into the set of real numbers, I immediately get the complex numbers simply by making sure I do cover in all of the things that I can build with it. So a complex number takes the form a plus bi, which basically says I have a real number a plus some real number multiple of I. And the way this is built is it's kind of like with a polynomial. I'm looking at all of the polynomials where x is replaced by the letter I. So we should lay out quick facts here. Since I is the square root of -1, I squared will be equal to, well, square root of -1 squared. The square cancels with the square root, giving me -1. If I have I cubed, well, this would be -1 times I, because I take the first two, group them together, become -1. So we'll just say minus I. And if I raise it to the 4th power, well, that's I squared squared. So it's -1 times -1, which is +1. It kind of it follows this cyclic pattern here. So if I was looking for, I don't know, let's say I to the 215. Well, all I'd really have to do is find out what the remainder is after I divide by 4, because every 4 powers gives just a 1. So I could actually split this up to I to the 212, because I know that one is a multiple of 4 times I cubed. Since this is a multiple of 4, I think that's 53. I to the 4th to the 53rd power times I cubed. This part is just 1. leaving me with I cubed, and up here I know that that's going to be equal to minus I. So the powers of I will always simplify like this. Now, I'm not going to do addition and subtraction with complex numbers because that's just going to be combining like terms, and we'll probably hit it incidentally when we do the more complicated step of multiplication. So let's just pick a couple of numbers. Let's say 2 minus 3i times 4 plus I. That should be good enough. So if I want to multiply these two together, then it works exactly the same way if I was multiplying two polynomials together, because I am using a letter here, so it works just like if I had 2 minus 3x times 4 plus x. With the caveat that right after I do my multiplication step, I'm going to have to do more work to simplify because I know that I is not just a variable, it represents the square root of -1. So we would FOIL this out or do all the distributions. I'm going to end up with 2 times 4 is 8 plus 2 times I minus 3i times 4, so that's minus 12i, and then minus 3i times I will be 3i squared. Then I combine like terms, so I've got 8 minus 10i minus 3i squared. If you did this on the version with the x, then you would just have x's in place, and you'd say, hey, I've finished multiplying out my polynomial. But here we know that since I is equal to the square root of -1, we know that I squared has to be equal to -1, and we can fill that in to further simplify. So we've got 8 minus 10i minus 3, and in place of I squared, I have a -1, giving me 8 minus 10i plus 3. So my final answer is 11 minus 10i. So that covers the basics of multiplication. If I wanted to do things to a power, well, then I would have to do that just like I would with polynomials. I would have to treat this as repeated multiplication. Multiply it all out, and then simplify it all the way at the very end. There is a, what should I call it? A theorem. Yeah, it's a theorem which provides a formula for doing powers a little bit more easily, or at least differently. Easy is up to the user, I suppose. But that requires us to go over sine and cosine, and I'm not ready to have that done quite yet. So after multiplication, we should take care of division, and we'll have a couple more things to do for fun. So the principal property of having a field is the ability to divide and still have a number which belongs to that field. So this is why the integers, we don't have divisions. We have, when we try to divide, we end up having remainders. But if we add in the extra numbers to have the rational numbers, suddenly division is possible or legal. Just like when we created the complex numbers, suddenly the square root of -1 was legal. So it doesn't matter what numbers we choose here. So let's do 3 plus 2i over 2 minus I. That'll be fun. So how do we divide this? We don't, actually. This requires something else. And that something else is going to be the conjugate, which is something we talked about when we had polynomials or when we were dealing with the quadratic formula, conjugates. So if I say z, which is the letter we use to say I have a complex number, if I say z equals a plus bi, then the conjugate is z bar, it's a little line on the top to say I'm using a conjugate, equal to a minus bi. And the power of the conjugate, z times z bar, is that when I multiply them, this is a plus bi times a minus bi, we now have what should give me the difference of perfect squares. So I'll get a squared, then I'll have minus abi and plus abi, so those cancel. And then at the very end, I'll have minus bi quantity squared. So it'll be a squared minus b squared times I squared, but I squared is -1, so a squared plus b squared. We need complex numbers in order to factor the sum of perfect squares. But what we should notice here is that this is a real number, which is important. In fact, it's a positive real number. And this is a tool we're going to use. But since I have these over here, I should also mention z plus z bar. As you might suspect, if I were to add these two together, all I get is 2a, which is twice the real part of the complex number and 0 for the imaginary part of the complex number. So we're going to use this in order to do this division. So 3 plus 2i over 2 minus I. And this is kind of like taking a step with fractions where instead of doing a division, you actually multiply by something else. So what we're going to do is we're going to multiply and divide, so top and bottom, by the conjugate of the denominator. And then what happens here is we'll deal with the top later. But on the bottom, we get the number, the complex number, multiplied by its conjugate. And over here, what that says is I should take the number parts and square them and add them together. But this is going to come out to 4 minus I squared, or 4 minus I squared. I squared is -1, so it'll be 4 plus 1, which is 5. And sure enough, 2 squared is 4 plus a 1 times I, so 1 squared is 1, so 4 plus 1 is 5. So what we've essentially done is we've taken our division problem, we use the conjugate to turn it into a multiplication problem. So I'll just leave this 1/5 sitting out in front. And I'll deal with this multiplication. So I'll end up with, let's see, 6 plus 3i plus 4i, and then plus 2i squared, so that'll be minus 2 actually. So I'll end up with 1 over 5 times 4 plus 7i. And if I really wanted it all the way in the standard complex number form, a plus bi, then I would distribute, so I'd have 4 over 5 plus 7 over 5i. So if I were to divide complex numbers, or try to divide complex numbers, that would require simplification by using the conjugate, so that the denominator is just a regular number, nothing fancy about it. and I can work through it until I get my answer in the standard form for a complex number, where I have the real part of 4/5 and the imaginary part of 7/5. So addition and subtraction, that's done by combining like terms. Multiplication works just like it did with polynomials. Division is the special one, but we can actually do more if we wanted to. For example, I can take square roots of complex numbers, and we've already seen that we can raise positive powers of complex numbers. That's just repeated multiplication. But let's try a square root. And this is the only level of root I'm going to attempt, because if I want to do higher roots, then we're going to use that theorem I mentioned earlier, but that's, like I said before, that uses sine and cosine, so that is a different class. Let's keep the numbers easy. So we'll do 1 plus I. We'll look for the square root of 1 plus I. And we're stuck already. All we can really do is say that this is equal to something which has been squared, right? So we're saying that a plus bi, if I square it, will be equal to 1 plus I. And that's really the best we can manage for this. Unfortunately, to some extent, well, if we find answers using the other way, the future way, there is a uniqueness problem. But fortunately, also kind of the way complex numbers work out is we're only going to have one square root of a complex number, as opposed to having two of them. I suppose, yeah, we'll have the positive version and the negative version, but there's nothing more extreme than that, despite complex numbers being kind of weird. So I'll just multiply this out. I've got I'll go ahead and put the plus or minus up there, but let's see, I'll have a squared plus 2abi plus bi squared. All right, that's a squared minus b squared plus 2abi. This is my standard form to work with. So what this is saying is that a squared minus b squared is equal to 1, and 2ab is equal to 1. This is a system of equations that I would have to solve in order to find the square root of 1 plus I. So you can imagine, just from guessing, if I had like a cube root or something, then this part of my work is going to be a lot worse. Fortunately, it's still possible to work out here. I can solve for b, so I'll say b equals 1 over 2a by dividing 2a from both sides. And then I plug that into the previous equation, so I've got a squared minus 1 over 2a squared equals 1. And I can solve this for a. So what I do is I just multiply through everywhere by 2a squared so that I don't have any denominators. And I wrote it wrong over here, so let's fix that. It's 2a quantity squared times a squared minus what I had here times 2a quantity squared would cancel and give me a 1. And then I've got 2a quantity squared over here. So it looks like I've got 4a to the 4th minus 1 equals 4a squared. And we want to solve this. So let's bring it up here. 4a to the 4th minus 4a squared minus 1 equals 0. So here's a polynomial I'm trying to find the answer for. Fortunately, this is one that can factor kind of nicely. I'm going to have 2a squared. Oh, no, I won't. My signs are wrong, and I wasn't being careful. So let's go ahead and write this with x's instead. So let me write this. We've got a squared equal to x. So I've got 4x squared minus 4x minus 1. That just makes it easier to look at. I'll just have to fix my answer in the end. And when I, let's see, when I do the quadratic formula, I'll have x equals 4 plus or minus the square root of b squared. So that's 16 minus minus 4 times 4 times minus 1, horrible, all over 2a, so that's all over 8. So I get x equals 4 plus or minus the square root. This is 16 plus 16, so 32, all over 8. And that would simplify, let's see, 4 plus or minus, that's 16 times 2. So I'll have 4 root 2 on top, all over 8, which reduces more. Give me 1 plus or minus root 2 all over 2. And this is my x value, which is equal to a squared. So my a is actually equal to, oh boy, the square root. There's a plus or minus here, but one of these we're not actually allowed to use under the square root because we're looking for real number answers. My a will be 1 plus the square root of 2 all over 2. I won't use the minus here because if I use the minus, I'll have the square root of a negative, which is not what I want because I know that a is supposed to be a real number, so I'm not allowed to count the complex number version. So this is my only answer for a. Technically there'd be a plus or minus there, but the plus or minus is already covered up here where I wrote it up there. Now that I have my a, I would plug this into the b, and I would put those together to give me my final answer for the square root. All in all, kind of tiring. So let's move away from the arithmetic of them. The real numbers and every number field below it follow a real line, right? We start 0 in the middle, and we work out 1, 2, 3, etc. And then in the negative direction, -1, -2, -3, in that direction. And the real numbers include everything in between. Well, we don't get to have a number line for the complex numbers because there's actually 2 dimensions to it, because it's got the real part and it has an imaginary part, which is kind of like having an x part and a y part. So complex numbers are often included kind of all at the same time when you're dealing with vectors and trig and other problems where we need to graph things. So we'll label this one with an R. Well, the complex numbers fit into a plane. We label them with a fancy C. So here we've got the positive real line. Let's make it green, actually. So here is R. This is the basis of the complex plane. We have the real line, kind of in place of the x-axis. And then on the y, or vertical axis, we have the imaginary part. So if I plotted a point somewhere, 1, 2, 3, 1, 2, right here, a point on the complex plane represents the complex number 3 plus 2i. if I have a negative value for my I, well, this is the complex number 1 plus, well, it's not plus anymore, but I'll keep writing it, minus 2I. Or I could write it 1 minus 2I. So because the complex numbers already fit in a plane, you really don't want to think about what a graph of a complex valued function looks like, because the input values fit in a plane and the output values fit in a plane, and altogether you'd be trying to graph things in 4 dimensions. You can try to think about that if you want, but it's not fun. However, we can keep talking about why we had complex numbers in the first place. So complex numbers they kind of fill in for missing roots or factors when real numbers cannot provide answers. So an example here is when I've got x cubed minus 2x squared plus x minus 2. Here's a polynomial. I should be able to factor this. I can factor it by grouping, or if I don't notice that I can factor it by grouping, I can try the rational root test. But since this factors by grouping, I'll see the first pair. I can take out x squared, leaving me with x minus 2. The second pair is already there, so I'll just write x minus 2, which works out to factoring to x squared plus 1 times x minus 2. If I did the rational root test, I would have seen that 2 was one of my roots, and I could have done long division to find out what that was. If I want to continue to try to find complex roots or complex factors or factor it into complex numbers, then what I would have to do is I have to take each of my irreducible quadratics, because if you remember, part of the fundamental theorem of algebra was that every polynomial with real coefficients can be factored into linear and irreducible quadratic factors. So I'll just take my irreducible quadratic factors and I will do the quadratic formula on them. So we've got here my x would be equal to plus or minus the square root of minus 4 all over 2. So x equals plus or minus 2 times the square root of negative 1 over 2. I get to cancel those. I get plus or minus I. Or basically I get 0 plus I and 0 minus I for my complex root answers. And since my number up here is 1, I get to get off easy. My factors are therefore x plus I and x minus I. And sure enough, if you multiply this out, you're going to get back x squared plus 1. So something I could ask you to do, and something some people have asked about regarding either the test or a quiz question, is we can verify, let's say x minus I is a factor of, and I'll use the whole polynomial here, x cubed minus 2x squared plus x minus 2. And this goes back to saying, what does it mean to be a factor? Well, if this is a factor, that means x equal to I is a root, which means if I plug in this root, I should get 0. So I'll write that, hence I cubed minus 2 times I squared plus I minus 2 should be 0. So let's go ahead and try that. I picked a pretty easy example here. So let's see. I cubed from before is equal to minus I, and I squared is equal to minus 1, and I is just itself. So I know that my answer here should be, let's see, minus I plus 2 plus I minus 2. So we got minus I plus 2 minus 2. I end up with 0 after I simplify all of that. So I know that that is a factor. Another thing I could have done to check if it's a factor is do polynomial long division with x minus I, but that looks really bad. So let me show you the first step of what that would look like. Let's see, I've got x cubed minus 2x squared plus x minus 2. And I mean, you could technically do this with synthetic division too, but I'd have x minus I out here. So I need x squared. Okay, so I've got minus, and I've got x squared times x is x cubed. X squared times I is ix squared. Okay, so that cancels to 0 there. I have minus 2 minus minus I, so that turns into 2 plus I parentheses x squared. And then it's just going to keep getting worse, plus x. And then here I need to put in plus 2 plus I x. So it can get really messy if you try to do it like that. I'd rather just plug in the numbers and see if when I simplify it, it simplifies down to 0, because that will mean that it is a root. That's all we have on complex numbers for now. In the next class, what I expect will happen, although I could be totally wrong like I was about complex numbers for this class, is after you cover sine and cosine, you'll talk about de Moivre's theorem for complex numbers and the polar representation for complex numbers. Not in that order. Polar representation comes first. And what that is it's a different representation for complex numbers on the plane. They use angles and distance instead of using the axes. And that kind of trivializes, in some sense, some of the problems you could have with complex numbers. For example, with exponentiating them or trying to find logarithms with complex numbers, which is not something you should try to do unless you have it in polar form. So since this is a bonus video, you do not expect to see this on a final exam, but it is a related topic for the extra credit I have created for this second midterm.